We're now going to visit a topic that all of you definitely have seen before, but we're now going to look at it from a different perspective. A function. A function in math, you should think of it as something that takes in an input and produces an output. The first time you study functions, you think of them as graphs, but now this is not a right approach in this course or in general in mathematics. This is a graph of a function and not the function itself. This might seem unnecessarily pedantic, but it is actually important to not use this approach for studying functions, especially in this course, because our functions are going to not be representable as graphs, as we will see. A function, for me, I always think of it as some black box that takes in some input and produces some output. As long as you have this setup, you have a function. Of course, you know functions from calculus and from high school algebra. So for example, you can have a function, let's say f of x equals x squared. Here it takes in a real number x and produces an output, which is a real number y, x squared. An algorithm is a function. And an algorithm can take in some input and produce some output. So a more concrete example could be a sorting algorithm. And it can take in as input, say, for example, an unsorted string like 312 and sort it and produce 123. You can even have a function that takes in a set and produces its cardinality. So for example, I can put cardinality here, and then it takes in a set S and then produces size of S. So the inputs and outputs can be very varied. So the input for cardinality is any set, and the output is a natural number or infinity. So you can have functions like this. So functions are very, very general things right next to sets. And there's no way for me to draw the graph of cardinality. What is the graph of cardinality function? What is the graph of sorting algorithm? So with that introduction, let's get into the details. A function f from x to y. Here, x and y are sets. Takes in an input little x, which is an element of capital X, and produces f of x, which is an element of y. And x is called the domain. So domain is the place where the inputs come from, and y is called the target. The set-theoretic way of describing a function is almost like a graph. F is a subset of x cross y such that for every x in x, there is exactly one y in y such that let me write this using the formal logical notation. So f is a subset of x cross y such that for every x in x, there exists a unique little y in capital Y such that x comma y is to f. You can also expand out unique, but it's complicated and it only makes it more confusing. So I'll stop here. So this is the set-theoretic definition of function. And let me give you some non-standard examples. I can take x to be any set. So x can be the set, let's say 1, 2. and y can be the set of all real numbers. And then all I have to do is for every value in x, I have to pick one unique value in y, and I can pick it anyway. So I can say that f is 1 comma pi and 2 comma e. And this is a totally valid function. And what this is notation is saying is that f of 1 is pi, f of 2 is e. And this is typically pictorially described as follows. So you have this x here, and you have this y here. Here my y is all real numbers. Here my x is the set 1, 2. So x has 2 elements in it. And I am then sending 1 to pi. And I'll draw arrows like that. So this is a pictorial way of representing functions. So now we have 3 different perspectives on function. You can think of it as a black box that takes in input and produces an output. You can think of it as a tuple, or you can think of it as this picture. So let me just highlight the 3 things. This is the black box picture. Takes in 1 gives you pi. Takes in 2 gives you e. You can represent it as a tuple, or you can represent it as a map between the elements of the set. Okay, so these are, we can start with the input output description. So this is the standard thing. We can say f of x equals x squared, where f goes from real numbers to real numbers. Actually, let me make this f goes from natural numbers to natural numbers. This will be easier to describe. From this, I can create a pair description as follows. I take every x, and then I pair it with x squared. So f is the set of pairs x and x squared, where x is a natural number. Okay, so that's the pair description. As you can see, this is exactly the graph. And this is a subset of n cross n. And if I were to draw it pictorially, I would draw it as follows. Of course, I cannot draw all of f because natural numbers are infinite, but I can at least do an approximation. So here are my natural numbers. F goes from n to n, and I have 0, 1, 2, 3, 4, so on, 0, 1, 2, 3, so on. And now f sends 0 to 0, f sends 1 to 1, f sends 2 to 4, f sends 3 to 9, 4 to 16, and so on. So that would be the pictorial description of this function. Now let me give you a non-example of function. So if I were to draw something like this, then this would not be a valid example. So let me just take 0, 1, and let me take these as 2, 3. F is a function from the set 0, 1 to the set 2, 3. I'm saying f is the set of tuples 0, 2 and 0, 3. And the problem is that there are 2 things which have input 0, and a function has to take an input and produce a single output. So you can't have one input going to 2 outputs. So this is a non-example. On the other hand, it is totally fine to have 2 inputs go to the same output. So here's an example, which is very subtly different. I'll take the same domain and targets, and now I'll map them like this. And this is okay because it's taking the input 0 and mapping it to 2. It's taking the input 1 and mapping it to 2. So here again, f goes from 0, 1 to 3. F is represented by this set. And this is a totally valid example of function. So these are functions, very simple things. But as with everything we have been doing so far, the devil is in the detail. As long as you stick to the definition of function as it is defined using sets, you should be fine. There's one concept we need to know here. And again, this is something you already know. The range of a function f to y is a subset of y given by all the y in y such that f of x equals to y for some x. This will be in the set builder notation. This will be written as range of f is the set of y. So the range is set of all the y's such that there exists some x which hits that y. And pictorially, if I had some domain x and some target y, and I have things like this, then these are in my range. And notice that this is a subset of y because I'm picking up elements of y. And a concrete example, if I take f to be the same function I had defined above, then the range of f here is the set containing the single element 2. Similarly, if I had the function from natural numbers to natural numbers that sends x to x squared, then the range is all squares. That is 0, 1, 4, 9, 16, 25, and so on. Now notice that the range depends on the target very seriously, or on the domain and the target both. So let me give you variants of the same function. I can take f from n to r, and I can define the same function, and here the range does not change. It's still 1, 4, 9, because the domain is still n, but now I can change the target and I can make it f from r to r, and now this changes completely, and now my range becomes positive real numbers. And so things that were missed by I should use different name. So things that were missed by f are no longer missed by g, because the domain of g is all real numbers. So that's the range. A simple concept. Every concept in this section is very simple. The key is, again, I keep repeating, it's in the details. You need to unlearn some of the intuition you have about functions and relearn it in set notation.